Okay, so this is our agenda. I'm gonna start now. So first of all, our little recap. Here's a few things you should already know. So some questions that we've gone through before is what do we run our code on? How many types of controller boards are there? And what sort of tests we do? And what do we do before merging into master branch? So we run all our code on an STM32 microcontroller. There are many different models, but we use the F0XX, or XX represents any sort of number. They're just placeholders, basically. But we run everything on F0 model. We have one type of controller board that we interface with, and this makes it easy to talk to any sort of hardware that the hardware team brings up. The different types of tests we have are unit tests, which we would test a specific module, smoke tests, which would sort of emulate someone trying to use the functionality from a certain library, and then integration tests where we have someone putting together a bunch of modules and trying to see if they all play nice together. And we always do code reviews before we merge into master. So basically, I think for people who've already done their firmware 102 homework, I'll be doing code reviews later probably. But what we generally do is we'll go through each other's code to make sure that we adhere to our coding standards, and also to make sure that the code works. That's really the main thing, is that we want to make sure that we don't run into weird bugs. For example, I know like Ryan was talking about Toyota once, and basically what happened was that their stack was overflowing, and this was sort of a weird error they were encountering, which caused a lot of issues in the car, and they couldn't figure out for like months. So we want to make sure to review each other's code to make sure that we don't encounter these sorts of problems. And sometimes these problems are hard to catch, which is why a lot of times you'll have multiple people look over the same piece of code. All right. I think you guys have gone through this already, but this is sort of what you've done in firmware 102. Basically, with your libraries, we have the interrupt library. You see at the top here, interrupt library, soft timer library, and the GPIO library. And these libraries each allow us to blink an LED. Here, we're basically just toggling the state of the LED constantly in a while true loop. We have a settings struct up here, which initializes the settings for the actual LED itself. So for direction, we want to be driving the LED basically. And for state, we want to start with, this is the initial state that we want our LED to be in, which is GPIO state high. In our case, with our LEDs, this would mean that our LEDs would be turned on. The alternate function thing, you don't really have to worry too much about this. You can set this to none, but we normally have to set this to like analog. So the GPIO pins can have multiple different functions. And so if we want an alternate function, we can specify that. And then this is just a resistor. So whether we want to specify if we want a pull up or pull down resistor to help drive the LED basically. So after our initialization here, we can run everything in infinite loop and just simply keep toggling the state. So this will, every few seconds, it'll keep flashing basically. So that's what this little piece of code does. And these all rely on libraries. So for example, as I said before, we have the interrupt library, the soft timer library, the GPIO library. And this makes our code a lot easier to write because you don't have to reinvent the wheel each time you want to, like, let's say, toggle a GPIO pin. Because we have this function here and it's written well, so you can simply just use this function. All right. The next part is more on our hardware libraries. So just now we saw a few examples of them. And I think, as I said, you guys have already played with them a bit. We have the GPIO library, the soft timer library, and the interrupt library, yes. So if you guys aren't familiar, there's something called GPIO, and this represents general purpose input and output. So on our actual microcontroller itself, we have these little pins, which can be basically, generally what we use them to do is, for example, we can output something. Earlier, we saw we could output to an LED, so we could set its state to high or low. This could also be used for input. So let's say we're trying to read the state of a button. Is the button pressed or not? We can configure our GPIO settings to read in data from these GPIO pins. And I also talked briefly about this, but there are also alternative functions, or also alternate functions that can be used. So these are more useful for our ADCs, which are analog to digital converters. Basically, instead of just having a 0 or 1, which was high or low, we can have a range of values that we can read in. So that's what our ADCs, as we'll see later, will help us do. So this is a very brief introduction to our GPIO library. The library itself has documentation. So if you go into firmware, like our firmware repo, and you go to gpio.h, so you can go to VS Code and search this up. If you guys are using VS Code, you press Control P. I think you should be able to just type in GPIO, and you should be able to easily find a file called gpio.h, which will have all the functions here. This is basically our interface, and it tells us how do we actually use this library and what does each function do. So I'll briefly go through this, but GPIO init will initialize GPIOs for us. Init pin will allow us to initialize a specific pin that we want to use. Set state, it's quite obvious. We can change the actual state of the GPIO pin itself. So do we want it to be high or do we want it to be low? GPIO toggle state, again, this is quite trivial, but basically all it does is if it's low, it'll switch the state to high. And if the state is high, it'll switch it back to low. And then we have GPIO get state. This is similar to what I was talking about earlier with like a button. We can simply read from the pin and see whether that pin is high or low. Another thing you guys should know about is PWM. So before we move on with the hardware libraries, I did mention briefly about something called ADCs, and they aren't actually reading a true analog value. And so let me explain. With PWM, basically what happens is that you'll have something generating a pulse. So this represents pulse width modulation. So something will generate a pulse with a certain duty cycle. So you'll see here the duty cycles are specified 0%, 25%, and 100%. And what the duty cycle shows is how much time or for how long the state is high in a given cycle. So we have the actual period here. This represents each cycle. You see the dotted lines. And then looking at the 25% one, you'll see that the pin is only high for about a quarter of the cycle. So that's what this represents. And what's interesting about this is that, let's say you have an LED and you want to control the brightness of the LED. Now, with the GPIO pin, normally what you can only do is you can either say, well, if I set the state to low, it'll be off. And if I set the state to high, it'll be on. But with PWM, what you can actually do is you can or you can keep toggling the state high really, 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 really fast at a certain, with a certain duty cycle, and you can actually control the brightness of it. So for example, if the duty cycle is 100%, it'll be fully on. If it's 25%, the LED will be like sort of dim, not all the way on, just a bit dim. And then when it's 0%, it'll be off. And I think there's a video here that better illustrates this. Does everyone see the YouTube link? Or does everyone see the YouTube video that I have with me on my screen? Okay, cool. I'm just going to play this a bit. And you can see this person is able to control the LEDs with a slider. Yeah, so that's the idea there. Basically, you can just move the slider to change the duty cycle, and then that'll let you control the brightness of the actual LED itself. All right, so finally, going on to ADCs. As I said earlier, the ADC represents the analog to digital converter, and this is what allows us to actually read analog signals. Oh, isn't that a potentiometer? Do you mean back here? This pulse width modulation?
No, I was just wondering, like, because the YouTube video had like I use that for like like my lights in my house, and that's like the same thing. But we use like it's just a potentiometer. I don't know how that's.
Uh, yeah. So the you can use a potentiometer to actually do the same thing.
Mhm.
Um, yeah, so the potentiometer is you can turn a knob and it'll control the resistance, right? So that's more of an electrical thing. For PWM, this is, I guess, controlled by the software. So you could do this without the potentiometer, basically.
Oh, okay, okay.
Yeah.
All right. All right. Thank you for explaining.
Yeah, no problem. All right. So are there any more questions before I move on? All right. I'll keep going for now. We can, if you guys have any questions, just toss it in the chat or unmute your mic or something. Okay, so going on to ADCs. I have this snippet of code here, which shows you briefly how to use the ADC library. And let me actually open it in GitHub. I actually edited this recently, or I guess back in June. But we have a new ADC library, which should make it pretty easy to use and read from an ADC. So we were just talking about potentiometers. And what we're doing here is we're actually reading the, I guess, voltage coming from something based off of that's going through a potentiometer. So this will be a variable voltage. So here we have our typical library initializations, interrupt, soft timer, GPIO. Here we specify the actual address that the potentiometer is connected to. So in our case, we have it connected to our board, GPIO port 8, pin number 0. And then we specify the settings. So this time the direction's in, and we're going to start off with low. We have no internal pull up or pull down resistors, but this time we have an alternate function. And we have to set it to analog to specify that we're reading an analog signal. So now we initialize the GPIO pin with that potentiometer address along with the settings. And then we can also initialize the ADC itself. Now, here, this is where we attach our, like, I guess we connect the ADC library to the GPIO library. But what we end up doing is setting a channel for this potentiometer pin. And this allows us to actually read data from, so it'll assign a channel to that GPIO pin, and then data will be fed to that channel. And so here, we're just going to be polling in a loop. We're going to be constantly checking. So we're going to be reading the raw data from that pin, passing in the address and passing in this pointer. This pointer will, so this pointer is going to be taken from whatever function, and the value that's in the pointer will be changed basically. Because you're like, I guess you might be asking, like, why don't we just return the actual data value? Because we have a function called ADC read raw pin. It's sort of, I guess it'd be easier if someone could just use this function and get the data from the return value of itself. But we don't actually do that because we have something called status codes. And these status codes help make sure that our function runs properly. So you'll see here that I run this function, and then I check if it equals status code OK. And this is done so that in case something goes wrong, we know that the values in here are invalid. So if this was not status code OK, then we would basically we'd be reading garbage here. So we shouldn't accept this data. And if we didn't do this check, we wouldn't know if the data in here was like returned to us was actually valid, which is why we have this if else statement. So if we do read it properly, then we can output the data to the screen. But if we don't, then we tell the user that we're unable to read that data. And then after this loop, we just add a little delay, about 200 milliseconds, and then we repeat this constantly. So, oh, I guess you guys, I don't think most of you, or I guess most of you are you guys in Waterloo right now? Is everyone back in person? Because the past few terms, like most people have been remote, but if you guys are in person, you could always, I guess, schedule a time to go in the bay and try this out with an actual board, I believe. But you can probably run this program on remotely as well. You just won't get any actual data, I don't think. So yeah, there's that ADC library. And this will come in handy because a lot of stuff encompasses, a lot of the code you write will use GPIOs and use ADCs. This is like the foundation of like firmware development on our microcontrollers. All right, so the next thing is an interrupt. So the interrupt library basically allows us to interrupt what we're doing. So you could be running some sort of code and then you would be interrupted. And the reason we want this is so we don't have to constantly poll for something. And I'll go back to this slide in a bit, but actually, yeah, here it is. But there's a waiting for mail analogy. So let's say you're waiting for, I don't know, some game to come in the mail, or you're waiting for a very important piece of mail to come. And there are two ways you could do this. So one way is you could constantly go out every day and you could check the mailbox to see if there's mail. So basically every day at like, let's say 9 a.m., you walk outside, you check your mailbox. First day, it's like not there. And you're like, oh, you're sad. You go back home. Second day, you go out, it's not there. You're sad. You go back home. And then finally, the third day, it comes. And you're like, oh, great. What an interrupt does is basically it'll notify you that your mail has come. So it could be any time of day. And you don't have to keep checking. That's the whole idea. So you could have spent that time in the first 2 days like doing other things, and it wouldn't matter because on the third day, you would receive a notification on your phone, or you would be interrupted, and then you could go out and retrieve your mail and then come back. And so some ADCs use this. Basically, the idea is that we don't want the ADC to be polling constantly for data, and instead, it'll rely on an interrupt. So when the data is there, you can just easily go and fetch it rather than constantly asking, is the data there? Is the data there? Is the data there? That's sort of the idea behind it. All right, any questions? Okay, if not, let's keep going. Section 3. So this part, I'll be going through a bit about how to read schematics in datasheets. This takes a lot of time. So it takes a lot of time to master because a lot of the language that's used in schematics and datasheets is very engineering-esque, basically. So there'll be a lot of these random technical terms where you'll be like, what does this mean? And sometimes you can't Google it because it's company specific or industry specific. But you'll learn over time, and I'll give you a brief introduction on how to actually find the data that you need. So first of all, schematics themselves are important. I think you guys learn, or if you guys are in like ECU, mechatronics or something, or even mechanical, I think you guys learn about like basic circuits, right? And schematics are important for this because a lot of times you'll be given these PCBs or random boards, and you'll be like, what's wired to what? And how is everything routed? How is everything connected? And how does my firmware fit into this? and sometimes there'll be crazy schematics. So this looks sort of like stuff you would see in like an exam, I guess, if the teacher wants to fail the whole class. So sometimes you'll have this crazy stuff, basically. And luckily, our schematics aren't like this. They aren't just all one big blob. What we normally do is we'd actually cut everything up into little modules so that you could isolate each thing and figure out what you need rather than having to look at one huge schematic that represents everything. Our schematics are at this link. Let me put it in the chat actually. So I don't think most of you guys have access to it right now, but if you'd like access, or if you're ever doing a project and you need access to the schematics for our boards, just send a message to Ryan, me, or Mitchell, and we can give you access to that. Hot glue, yeah. Hopefully you don't end up doing that. But hey, who knows? It's a design team, so weird things can happen. But please do not put hot glue on this PCB. Anyways, this is how the actual page looks. As I said, I don't think you guys have access yet, but I'll just show you briefly. And let's say we want to look at our BMS carrier and see what's going on. So we can go to our file here, or our folder, BMS current sense. And we can find the latest revision of the board. This is what hardware uses, and they'll always have new revisions. So this is pretty outdated already, but this is still a good example for firmware 103. And then you click in and you'll see something like this. And this is what I meant by each module is separated. So it's not all connected in one big blob, but each thing is sort of cut up so that you can easily see what's connected to what and why it's labeled as such. So in most cases for firmware, we're concerned about our controller boards, and you'll actually see the controller board down here. So let's take a look at that first. Oh. Let me give you some background, actually. So the BMS carrier itself and BMS current sense, the whole idea is that we don't want our battery to blow up, because the battery, similar to like, think of like your computer or think of like an iPhone, as it's running, things will heat up. And if the battery gets too hot, it can cause a lot of issues in the car. So how do we solve that? We use fans. And these fans just help cool the battery and make sure that our battery doesn't explode. So let's say we want to figure out where are the fans connected? Because we're looking at the BMS board right now. So where are the fans connected, and like how many fans are there? So let's look at the controller board. Looking at this, we generally want to check the labels. So, oh, look at this. PA10, so this is port A, pin number 10, fan enabled. So we're enabling the fans here. This looks like we're generating a PWM signal. So similar to LED, we can control how fast the fan is running with a PWM signal. That's sort of my guess just from looking at this. And then finally, it looks like we have PB4 fan sense, PB3 or PB10 fan sense, fan 3 sense, PB11 fan 2 sense, PA8 fan 1 sense. So this is great. You know, they tell us the exact GPIO port and pin that we need to talk to read the data. And we know how many fans there are, because there's obviously 1, 2, 3, 4. So that's all on, oh, yeah, you guys see where this is? Yep, okay. So we can continue tracing it out and see where the fans connect to. And so we'll notice that each fan sense is connected to one of these relays, and these fan modules. So this is basically the part number for each fan. And let's say we want more details on how do we actually talk to the fan itself and how do we interface with it. We can actually look up the part number itself, probably a DigiKey or something, or like Mauser, and we could actually find how do we actually interact with this fan. This is another part of the fan sense. So where are we actually reading from? And we have the resistor here, two fan sends basically. So I've gone through this briefly. I'll show you the data sheet a bit later, but we know there are 4 fans. We have 1 PWM pin control to control all the 4 fans. And if we want more specifics, we can look at the data sheet. So here I included the link, but as I said, if you didn't have the link, you would probably have to just check the part number on DigiKey. And I guess I'm not going to click it, but you guys can see this in your own time because I've already have a screenshot of it here. So in this data sheet, we can actually get details on each fan. So we know that these are 4-pin 5-volt PWM fans, and we know what each wire is connected to. So when you're actually in the bay and you see some fans, you know, like, oh, the blue wire is for the PWM signal, the green wire is for the RPM speed signal, and then you have yellow for a 5-volt line, and then black for ground. So these are some sort of details that you might find useful, especially if you're working on the closely with hardware and you're actually in the bay. And also down here, these are the actual RPM speed calculations. So these help us figure out how fast we need to, or how many pulses we need per rotation, and like what the duty cycle we need, or we should set it to, basically. All right. So finally, we have our last section, which are drivers. Basically, every microcontroller has a different way to interface with it. So each microcontroller is written differently. And a lot of times when you're using microcontrollers, you have to write to like registers and do a lot of like bit shifting and like toggle some random registers, which you have to always refer to the datasheet to know about. And this is sort of a pain, which is why we have drivers to help us take care of this, basically. These are examples of, I guess, part of the microcontroller on the board that helps drive everything else. So these are examples of a few of the PCBs we've made in the past. So the drivers themselves are very similar to the interface, but what they do is they let us basically drive the electronics and drive everything we need to do. Basically, what we have is we separate the code for easier use. So we want to separate the code from the actual electronics so that we can focus more so on the actual coding itself, rather than having to deal with registers and like bit shifting. I guess you could say that's coding as well, but we want to make libraries and drivers to handle this for us. For example, like GPIO, we don't want to have to deal with manually figuring out how to use GPIO when we can have a driver do that. So for example, in MCP2515, this is our CAN controller. So this basically helps us send or receive CAN messages. And we've shrunk everything down. So there's actually a lot that goes behind the data sheet, but we've shrunk it down to really 3 functions. Basically, all we really need is to initialize it, register callbacks, which basically allows us to receive the CAN messages and then transmit CAN messages as well. So it's really these 3 things that we need. And it just helps simplify things. All right, so conclusion. We have our main hardware libraries, such as GPIO, our soft timer, ADC. We briefly went through how to read data sheets and schematics. And we also went through what a driver is and why we use them. So for firmware 104, I believe, we'll be going through CAN, which is controller area network. And this is the main form of communication we use in the car. We have CodeGen, which helps us generate our DBC files, which help us decode these CAN messages. And then we also have I2C and SPI, which are both different communication protocols that are very commonly used in embedded systems. And finally, you guys have some Firmware 103 homework. So as I said in the beginning, you guys, I think you have to complete the Firmware 103 homework before we can assign you a task. So here it is. First thing is just the schematics and datasheet scavenge hunt. I have the solution for this. So once you guys are done, this just send it me a message and I can check your homework. And then part two is the actual code. So I think this project is just reading from an ADC every time someone presses a button, basically. So every time the person presses a button, we log some value and output it to a stream. So yeah, are there any questions?
For the homework, do we need Altium or like is that just a later thing?
Oh, no, yeah. So Altium 365, you probably only really need this if you're working close to the hardware or you're working on a certain board or something. But for the homework, you won't need it. Don't worry about it for now.
Yeah, because it was saying that we need to send our email to Ryan or Jess. So I was like, do we need to do that now?
Oh, uh,
No, no,
yeah,
yeah,
no, it's fine. Just leave it for later. Like you'll know when you need it.
yeah, for sure. Thank you.
No problem. Any more questions?
Actually, I hear someone else was let me just check the Slack. Was gonna do a help session for Firmware 102 Git problems, and it was a Discord. I think it was supposed to be on. Like,
Yeah.
and I'm not in the program, like the design team Discord. Is there a link like somewhere specifically on Slack?
Uh, I think Mitchell will reshare it, but if he doesn't, after this, because so Mitchell told me after I'm done from our 103, I should message him. So I'll let him know, and I'll get him to share a link
All right,
in the firmware Slack channel probably.
all right, perfect.
All right. Anything else? Since this is just a little like I guess info session, or I guess training session, I'm assuming everyone will probably have more questions once they actually start doing the homework and they're like, oh, how do I actually use the ADC library, or like how do I use this GPIO library again? And there is the firmware 103 notes that are all here with the link I sent. So if you guys are curious, you can look at that. Everything I've talked about should be here. Oh, except I'm going to update this right after the meeting because this is outdated. I updated my slide, but not this yet. But other than that, everything else, if you guys have any questions, just send Ryan, me, or Mitchell a message on Slack and we'll get back to you as soon as we can. And I think, as I said, I'm going to do a bit of code review right after this. So if there's no more questions for now, I'm probably going to end the training session. So thanks for coming, everyone. And I hope to see you guys on the, I guess, weekly meetings. And I can't wait to have everyone on the team. All right. No problem. I'll stop sharing my screen. Take care, everyone.